Finishing up our discussion on magnetic field, let's have a couple of examples. So let's have sample problem number 1. A particle decays by transforming into an electron and a positron. A positron is basically an electron but with positive charge. Suppose the decaying particle is at rest and inside a uniform magnetic field of magnitude 9.57 millitesla. And when the particle decayed into an electron and the positron, the two particles, the electron and the positron, move away from each other, move away from the decay point, in paths lying in a plane perpendicular to the magnetic field. This tells us that not only are the velocities of the electron and the positron opposite in direction, they move away from each other. The velocities of these two particles are both perpendicular to the magnetic field. How long after the decay do the electron and the positron meet? How much time will pass by before the two particles will meet? We are looking for time t. The magnitude of the uniform magnetic field, let that be B. B is equal to 9.57 millitesla or 0.00957 Tesla. The electron charge we know to be negative E, negative 1.602 times 10 to the negative 19 coulomb. The charge of the positron is just like the charge of an electron but opposite in polarity. So the positron charge is equal to positive E, positive 1.602 times 10 to the negative 19 coulomb. The positron and the electron are identical, same for the polarity of their charge, which means they both have the same mass. Mass of the electron is equal to the mass of the positron, 9.109 times 10 to the negative 31 kilograms. The original particle is at rest when it decayed. So initial velocity or velocity of the particle when it decayed is 0. The speed of the original particle, V0, is equal to 0. The velocity of the electron is perpendicular to the magnetic field. So the angle between them is 90 degrees. The same goes for the positron. The velocity of the positron is perpendicular to the magnetic field. The angle between them is 90 degrees. Again, we are looking for time t, time that elapsed before the two particles will meet. How long after the decay do the electron and the positron meet? So we are looking for elapsed time t. We know what happens to a particle, to a charged particle that moves in a uniform magnetic field, and the velocity of the charged particle is perpendicular to the magnetic field. The uniform magnetic field will apply force on the moving charge, and this magnetic force will act like the centripetal force. The charged particle will move in a circle. In particular, the charged particle will undergo uniform circular motion. We expect the same thing to happen with the electron and the positron since they are moving inside a uniform magnetic field and their velocities are perpendicular to the magnetic field. So the electron will undergo uniform circular motion. The positron will undergo uniform circular motion. Performing analysis using conservation of momentum, you have original particle decays into electron and positron. the momentum of the original particle is just equal to the total of the momenta of the electron and the positron. Momentum of the electron plus momentum of the positron. The original particle has initial velocity or has velocity of 0, which means momentum of the original particle is equal to 0. So 0 is equal to momentum of the electron plus momentum of the positron. This equation tells us that the electron and the positron have the same speed. They are moving in opposite direction, but they have the same speed. We can cancel out mass since ME is equal to MP, which will give you VE is equal to VP. Speed of the electron is equal to the speed of the positron. Now, the magnetic field will apply magnetic force on the electron and on the positron, causing them to undergo uniform circular motion. The force magnitude experienced by a charge moving inside a magnetic field is given by F is equal to absolute value of Q naught, VB sine phi, applying this with the electron. So you have magnetic force magnitude experienced by the electron is equal to absolute value of the electron charge times speed of the electron times magnetic field B times sine 90 degrees, the angle between the velocity of the electron and the uniform magnetic field. If we do the same thing with the positron, if we get the magnetic field magnitude experienced by the positron, we get absolute value of the positron charge times speed of the positron times magnitude of the magnetic field times sine 90 degrees, 90 degrees being the angle between the velocity of the positron and the magnetic field, since VE is just equal to VP and QE, absolute value of QE and absolute value of QP, they are equal, meaning Fe is just equal to Fp. The magnetic force magnitude on the electron is just the same as the magnetic force magnitude on the positron. Since the magnetic force is acting like the centripetal force, the magnitude of the centripetal force experienced by the electron and that experienced by the positron are equal, meaning the electron and the positron being subject to the same centripetal force, they will undergo basically the same circular path. They will take the same circular path as they undergo uniform circular motion. Since they undergo the same circular path and they are moving away from each other, they are basically moving in the same circular path but opposite direction, which means they would have the same period of the circular motion. Same circular path, same speed, same period. If the electron will take 10 seconds to make one circle, the positron moving in the opposite direction will take the same time to make one circle. They have the same period, which means the two particles will meet on the opposite side of the circular path. They will meet halfway in their circular motion, which means the time it will take for them to meet will be half of the period. So again, because the two particles, the electron and the positron, will be subject basically to the same centripetal force, but they have opposite velocities. The electron will undergo uniform circular motion in this direction. The positron will undergo basically the same uniform circular motion, but in the opposite direction. So they take basically the same circular path, but in opposite direction. Same centripetal force, meaning they will have the same period. So if it takes the electron 10 seconds to make one circle, it will take the positron 10 seconds as well to make one circle. So as the electron is moving, the positron is also moving at the same rate. They will meet on the opposite side of the circular path. Basically, half of the circular path. So that means the time that they will meet is half the period. So T is equal to period divided by 2. Using the period of the electron is 2 pi m divided by QEB, absolute value of QE. We know mass of the electron, we know the uniform magnetic field magnitude, we know the electron charge. We are able to calculate the time it takes for the two particles to meet. T is equal to 1.867 times 10 to the negative 9 seconds, or 1.867 nanoseconds. And then we have sample problem number 2. A .85 copper rod rests on two horizontal rails 1 meter apart and carries a current of 65 amperes from one rail to the other. The coefficient of static friction between the rod and the rails is 0.5. What is the magnitude of the smallest magnetic field that puts the rod on the verge of sliding? Mass of the copper rod is m, 0.85 kilograms. The two rails are 1 meter apart, which essentially gives you the length L, since this will be basically the length of the rod that carries the current of 65 amperes. Current 65 amperes, let that be current I is equal to 65 amperes. There is friction between the rod and the rails. The coefficient of static friction is given 0.5. And we are being asked to determine the magnitude of the smallest magnetic field that puts the rod on the verge of sliding. So we are looking for magnitude of the minimum magnetic field. Now, there are four forces acting on the rod. We have the magnetic force, which is applied by the magnetic field on the copper rod. The copper rod has current flowing through it. You have current carrying conductor. Magnetic field will apply force on the current carrying conductor. You have magnetic force FB. There is static friction between the rod and the rails. So you have static friction Fs. The rod has mass, therefore the rod has weight. The rod is resting on the two rails, so there is normal force acting on the rod. Since the rod is just resting on the rails, you have static case. F net is equal to 0. So F net is equal to 0 is equal to magnetic force plus static friction plus weight plus normal force. This is a vector equation, so we use our component method. to analyze that equation. You have the y component and the x component. The y component will tell us that the normal force magnitude is just equal to the magnitude of the weight. N is equal to mg. Whereas the x component tells us that the magnetic force is the one that is opposing the static friction, or it could be the other way around. Magnetic force is applied on the copper rod, which will cause the rod to slide. That will be opposed by static friction. In any case, x component tells us that the magnetic force is just equal to the static friction magnitude. And maximum of the static friction is given by mu s n. Magnetic force is equal to the maximum value of the static friction. Any greater than this, the rod will start sliding. And since the normal force is just equal to mg, Fb is equal to mu s mg. Fb is magnetic force magnitude. Magnetic force experienced by a current-carrying conductor. We know the equation for the magnetic force applied by a magnetic field on a current-carrying conductor. The magnitude of that magnetic force is given by ILB sine phi. Since Fb is equal to mu s mg, Fb equal to ILB sine phi, we have mu s mg is equal to ILB sine phi. Isolating B, we are looking for the magnetic field. So isolating B, B is equal to mu s mg divided by IL sine phi. We know mu s, we know m, we know g, 9.8 meters per second squared. Acceleration due to gravity. We know I, and we know L. We don't know sine phi, but knowing mu s, m, g, and I, and L, knowing these variables, we see that the magnetic field will simply depend on phi, particularly sine phi. We are looking for minimum magnetic field. The magnetic field will be minimum if the denominator, in this case, if sine phi is maximum. Maximum of sine phi is 1. That tells us that phi is just equal to 90 degrees. So setting phi to maximum value will give you minimum magnetic field. So setting phi to the 90 degree value so that sine phi is maximum. Maximum denominator will give you minimum magnetic field. Plotting in the value, we get the minimum magnetic field magnitude. B minimum is equal to 0.064 Tesla or 64.077 millitesla. And that's it for our discussion on the examples part. That's it for our discussion on the topic of magnetic field. So thank you for watching.